Welcome to OPC Day 2023. My name is Jim Luth. I'm the CTO of the OPC Foundation, and I'm also a system architect with Schneider Electric. Today, my presentation is on the topic of OPC UA as an information modeling language. So let's talk about what I'll cover in my talk today. I'm going to start with a discussion about the typical approach developers take when they're attempting to create an OPC UA product and why the information model is often an afterthought. Then we'll skip to a use case where there's a need to contextualize data in a place where there may be no reason to be moving the data itself with an OPC UA protocol. So the example I'll go through is to contextualize data in the cloud. And this data could be any data, not just automation data. Next, we'll take a step back, almost 20 years now from when we designed OPC UA, and we'll talk about what some of the design goals were for that meta model and how we applied some well understood computer science concepts to get where we needed to be. Then we'll talk about applying the UA meta model, in that case without UA communication, and how that's made possible by the layering of and decoupling of the UA specifications. And lastly, we'll talk about the possibility of using the UA model directly versus translating it to other technologies, and what some of the concerns and limitations are in that conversion, and any losses that might occur in that. And lastly, we'll draw some conclusions from the discussion today and think about how the meta model can be used going forward. So developers that end up developing OPC UA products often start out with the task of choosing an automation protocol for the factory floor. And in doing so, what happens is there's plenty of automation protocols that can be chosen, and they do a research project and they figure out the pros and cons of any number of industrial automation protocols. So for the sake of our argument, let's assume that you've looked at all this and decided OPC UA is a great thing, so I will use an OPC UA protocol and the OPC UA information model on top of that to convey my data. Once they've done this, typically what will happen next is they will implement a UA client or server. They'll choose one or more base information models that we offer that have been in the UA specification since the beginning: data access, alarms and conditions, historical access. And maybe they'll even go so far as to choose another protocol, or sorry, choose an additional information model from our catalog of industry information models, of which there are many. If you look at all of the organizations that OPC Foundation has partnered with over the years, we've created vertical market information models for everything from kitchen equipment, winemaking, robots, transportation, machine tools, you name it. And so these vertical market applications are all conveyed in additional information models, and sometimes people will implement one or more of those. And then finally, the task is sometimes a vendor will have a few extra things that don't show up in the models, the information models they've implemented. So they'll add some extra properties to some objects or variables that are basically thrown in at the end. But in general, the people developing the clients and servers don't do more than that. They're done at this point. They ship a product. It's a perfectly valid OPC UA product. It implements information models that already exist. But what they're missing out on in this case is they haven't done any real information modeling for themselves, and they haven't looked at exposing their existing data in the natural way, in its natural information model. So the issue is that in approaching OPC UA as a protocol, the people that end up implementing OPC UA don't gain the full capability of OPC UA because they're not looking at it from an information model point of view, they're looking at it as a protocol. So what I'd like to do now is talk about, essentially the rest of the talk is, what if we approach OPC UA not from the protocol end, from the bottom, so to speak, but approach it from the top, where we look at just the information model first. And I'll even go through examples where we don't use the protocol at all. So before I go into how to use the OPC UA meta model without the protocol, I wanted to talk a little bit about where, or a use case where you might actually use something like OPC UA without using an OPC UA protocol. So the case I want to talk about here is the case of big data in the cloud. So let's assume you've amassed a bunch of data in the cloud without a lot of metadata, without any real contextualization. It probably didn't come from OPC UA. It may be a bunch of real-time data that was stored. It might be unstructured data. It could be flat files, databases, records of various types. But assuming that it's already landed in the cloud and your goal is to do big data processing like artificial intelligence, machine learning kind of stuff, what you'll find pretty quickly is the data, raw data without any metadata is pretty useless, and things need context to be able to be analyzed. And so the issue often becomes relating different pieces of data you already have to each other to provide that contextualization. And so what I want to go through then is how you might use something as generic as the OPC UA meta model to create that types of contextualization on data like this in the cloud, where you won't be moving it at any point in time with an OPC UA protocol. So let's step back in time, almost 20 years ago now, to the point in time where we set out to design OPC UA from the ground up and choose a meta model for our work. We had two main goals in that. They were pretty lofty goals at the time. We wanted to allow any real world system that might be found in a factory or somewhere else, but we were very much focused on the factory floor and automation. We wanted systems to be modeled in a natural way without compromises or limitations. That is, if you could organize things in a natural way, you know, this pipe's connected to this valve has spare parts here, this connects to some other device via some protocol. Anything that you might want to model needed to be done in a natural way, in an obvious way. The second design goal we had was we wanted to allow any standardized model that was created by OPC or by others to be extendable by vendors in a way that does not break conformity to the standard model. So we wanted vendors to use a model that was well established for interoperability and compatibility purposes with others, but at the same time, we didn't want to stifle innovation and make everything in OPC UA a commodity by making everyone conform to doing things exactly the same way. And as a corollary to that, to be useful, we wanted all of those vendor extensions, the ones that nobody knew about until the vendor decided to create their information model, to be discoverable and interpretable by clients without a priori knowledge to the extension. So picture, I wrote an OPC UA client 10 years ago. A vendor this year decided to extend an existing model and add his vendor extensions. My 10-year-old client should be able to discover and understand the extensions from the vendor and use them. So if we could do these two things in OPC UA, we decided we would have the right design. So to address the second goal, that was the standard model that can be extended by vendors, we latched on to the notions made popular in OOP, object-oriented programming. In object-oriented programming, the data for an object and its methods are all encapsulated together, and there's a notion of types for objects and instances of those objects, and the types can be derived from base types, and base types can be extended with new information without violating the contract that is the base type. So the object-oriented programming paradigm was chosen to be the paradigm in OPC UA as well, partly because even 20 years ago, object-oriented programming languages were becoming more popular, and developers that would potentially be writing OPC UA clients and servers understood those OOP principles. So we followed all of the rules for OOP. Of course, we're not using or creating a programming language, but we're creating an information model using the same constructs. So in OPC UA, we have OPC UA object types, and then we can create instances of those objects, and those objects can encapsulate variables, methods, and events, all related to that particular object. And what variables it has, and what methods it has, and what data it has is all part of the definition of that object type. So we gain all of the features of OOP, abstraction, encapsulation. We make heavy use of inheritance and the polymorphism that gives us that ability to call the base class and act as the base class, even if I don't pay attention to the extensions. At some point later in OPC UA, not with the original design, though, we even added another OOP concept of interfaces. And interfaces, I won't get into much here, but it solves some of the problems of multiple inheritance, and again makes it easier to modularize functionality in something that's less than an object in a derivation tree. So this is nice. We can have variables and methods and events all associated with objects, but unfortunately this doesn't go far enough for what we need, because we also need to be able to relate one object to another object, or one object type to another object type, without strictly the containment of encapsulating these things into an object. So for that, we had to move on to yet another technology. So to describe the way OPC UA objects relate to other objects, we turn to another well-known computer science paradigm, that is the database model. There are a number of database models. Most people are familiar with the relational database model, and that's quite popular, with SQL databases. But we have found that the relational data model has inability to easily and directly model real-world relationships. So we studied other database models, and we settled on to reuse the concepts of what's known as a network model database. So a network model database is quite interesting. The history of this is it was conceived in the 1960s as an improvement to a hierarchical database, and basically it's a relatively simple concept in that records, which are noted here as these circles, are related to other records through links, and these links can be one-to-many, many-to-many, and in the network model database, a child, or a member as it's known, a member record can have more than one parent. So here we see D2 has two parents, C1 and C2. With this ability to relate records together, in any arbitrary fashion with one-to-many and many-to-many relationships. It turns out with this kind of a construct, there's no real-world uh, system that you can conceive of that can't accurately be modeled. Um, the network model database turned out never to be terribly popular, and it was superseded or overshadowed, I should say, by the SQL or the relational database model, simply because the relational database model was more efficient to query and to actually utilize in practice. Um, but the network model database actually has some very significant advantages, especially when it comes to modeling. And this is having somewhat of a reincarnation today in the NoSQL database push that you hear about, and essentially a slightly modified version of the network model database is known as the graph database model. So things like um, Microsoft's Cosmos database, as an example, in the cloud is a graph database, much like this. So we basically repurposed these concepts of the network model database, and we went ahead and applied that to OPC UA. So the terminology is slightly different, and we don't call it a database, yet this is where the paradigm comes from. So in OPC UA, the records of a database are the nodes in the UA address space, and the nodes themselves are either objects or variables, or object types or variable types, as in for us the metadata or the type system and the instance system are all appear in the same address space as nodes. So you'll hear that term in OPC UA of nodes. And then the links in the previous example with the terminology of the network model database become UA references. So the lines between the circles in the previous diagram are those references. And in OPC UA, the references follow much like the objects or the circles that they connect, also follow the OOP model, in that they can be they're typed and therefore can be subtyped. So I can start with a reference type that says, oh, this is a hierarchical reference, and then I can say, oh, this is a special hierarchical reference that like has component or organizes or something else that has increased semantics, right? Following all those same rules that doesn't violate the ISA relationship of the parent type. So some other characteristics of references, some binary capability of them. Every reference type, I should say, is either symmetric or asymmetric, and every reference is either hierarchical or non-hierarchical. And then from there, the derived types add more specialization to those things. So with that, we combine the network model database concepts with the object-oriented programming concepts, and together now we have the meta model for OPC UA that can describe any organization of data of any complexity with all of the design goals that we set out for. Notice that by combining these two very generic computer science level concepts, object-oriented programming and the network database model, there's nothing about the meta model in OPC UA that has any direct or even indirect relationship to automation data or protocols or anything that would somehow restrict its use to the industry that we typically find OPC UA in. And it's this generic nature of the OPC UA meta model that makes it appropriate for other uses, in particular when you separate the protocol from the information modeling. So we use various diagramming techniques to try to visualize the OPC UA address space and its capabilities. This is an early attempt at at such a diagramming notation. So what's shown here is the notion that we have object classes. That would be the type layer here that you see. The circles or the ovals here represent the nodes in the UA address space, or what would have been the records in the um, network model database. The lines between the nodes, of course, are the relationships, the UA reference types that we've talked about. And again, in the same address space, we have all of the types involved for the objects, and we have the instances of those objects. And here you see the different line styles. So instantiation between layers here, this would show that this is an instance of this type. You have other relationships to data type references and so forth. Um, and all this appears in that browsable address space in OPC UA. So again, trying to diagram this, it gets complicated quickly. This, like I said, was an early attempt at that notation. We've since actually standardized on a standard notation. In this case, we've used the UML notation as the basis and created our own derivation of that. It's what in UML is known as a stereotype. So there's a UA stereotype for drawing OPC UA drawings depicting the address space. And so you can see some of the conventions here. We have objects and object types. So all the types in the type systems have the drop shadow. The instances have no drop shadow. The different shapes indicate the node class. Objects are slightly different than variables, and methods, of course, are different as well. And then the reference types themselves. Some of the reference types have special arrowheads or notations on the endpoints. So for some of the commonly used types like has component and has property, we have special forms. In other cases, for all the other reference types, the convention is to just write the name of the reference right on the line. And then you see other things. The double arrow is the double filled arrow is for symmetric references. The single filled arrow is asymmetric reference, and then the open arrows are hierarchical references. So again, there's a lot of detail to this and how it all goes together. You can find this notation is defined in the appendix of Part 5 in the spec, and all the rest of the specs, of course, build on that and use that notation to describe the information models that they use in those parts. So hopefully I've convinced you that the OPC UA meta model, as it was designed, is sufficiently generic to describe any kind of information, any kind of relationship between objects, and is sufficient for the use case that we described. But the question remains, how do I use that meta model in a way that is separate completely from the OPC UA communication? And the key to this is that the OPC UA specifications themselves were written in a way to be layered and completely decoupling things like the concrete encoding and protocols from the model and the meta model that is OPC UA. So what you'll find is that we consider parts 3, 4, and 5 of the specification to be abstract, and that is they lack any connection to those underlying technologies. We don't talk about TCP, we don't talk about big endian and little endian, we don't talk about structure packing, serialization formats, and so forth. It's all just pieces and parts to describe the building blocks, but you can't build anything consistently by just reading the abstract part. Part 6 is the part where we actually do those mappings, and we map things to protocols and encodings. And this layering of the spec allows the parts to be used separately. And in fact, what I'm proposing is the meta model defined in Part 3 can be used with any technology you desire, right? Not just the mappings in Part 6. So it's reasonable that someone could create an OPC UA meta model that relates data in databases in the cloud and never talk about any of the things about transporting the data using the mappings in part 6. So now that we've determined that OPC UA can be used to provide this context information without using the OPC transport, the question is, should you? And what other technologies might you choose to do a similar task? Well, we've already talked about or mentioned at least, the graph database model. So a modern graph database would have many of the features that the network model database does, that the OPC UA meta model is based on, and it in fact would be a reasonable way to provide context in the cloud. So that would be one choice. Another popular technology is the semantic web technology from the W3C. This is based on two of their pieces, called one called Resource Description Framework, or RDF, and the other one the Web Ontology Language, or OWL, that builds on top of RDF. The diagram here on the right is an OWL diagram depicting the relationships between entities in the semantic web. And so OPC UA is not certainly the only technology that can be used to render an information model in this way and provide that contextualization. And the issue is, you could also consider defining an information model in one of these languages or technologies and then translating it to another for implementation. And that in itself brings up some other questions. So the complication is that each of these technologies has a slightly different meta model that they start with. And in converting from one model or one technology to another, the lack of identical features means that the translation isn't necessarily one-to-one, and you don't end up with a sort of a natural view that matches the other. So each model typically can be adapted to represent the other with reasonable fidelity, but there was often, as an example, some glue objects that end up appearing in a translation from one to another. So as an interesting example to that, some of these technologies allow properties to appear on references. And in OPC UA, properties aren't allowed on references. And so if we were translating from one of the technologies that had properties on references, in OPC UA we would have to put intermediate objects between references to represent and hold those properties. So you don't get the model mismatch means the translations don't come for free, and sometimes they're not pretty. So the choice of which language to model in, it really does, in a sense, drive a choice, and you have to make a reasonable choice for why you model in one language or another. Modeling in OPC UA, of course, has the advantage if the data is coming, as an example, from the field in OPC UA, and you have a model that's already there, then preserving that model has some value. We have a working group, subgroup of the OPC UA working group, working on semantic validation, and that group has actually done some work on mapping OPC UA to OWL as an example. And this was done in particular to take advantage of some of the advanced tooling of the OWL tool chain, where they were able to do some validation reasoning over the OPC UA model, but to use those tools, the model itself had to be first converted to OWL. So to wrap up my presentation, let's take a look at what we conclude from this. The OPC UA meta model can in fact be used to create information models in ways that never use the OPC UA protocols to move any data. The meta model is sufficiently generic to describe any reasonable association and metadata around data and relate things together. OPC UA is certainly not the only ontology language or technology for ontologies that could be used, and others may be more appropriate in different environments and situations. Thirdly, we've concluded that with careful adaptations, you can convert from one ontology language to UA and back. not often with necessarily without caveats and careful work. And lastly, and this is something that I think you'll see more of in the future, but as UA technology are used more and more in the cloud and more and further away from the factory floor where UA got its start, the OPC Foundation needs to provide more standards or guidance or best practices that describe the translation of UA information models into different formats for different purposes. And we've just sort of scratched the surface here of what some of that might be with our cloud initiatives. We'll be spending more and more time on this topic as time goes on. Thanks for joining me today. And stay tuned for our next presenter, Wolfgang Manke, who will give a more practical talk on best practices for OPC UA information modeling.